Hello. So you are watching this video on either Tuesday or Wednesday evening, afternoon. We just talked about using rectangles and trapezoids to estimate area under a curve between the x-axis and the function itself. And so that, while is a good estimate, is not exact. So in this video, we are going to get more precise with finding the area between a curve and the x-axis by using the limit definition of the integral. On Thursday and Friday, we are going to get even more efficient with precisely evaluating integrals using something called the fundamental theorem of calculus. So, first thing we have to talk about is formal notation of an integral. So, with an integral, we have this. An integral we think of as the area under a curve. And the integral is signified by this curvy S shape. And it has a couple of pieces. So on the bottom here you have little a, and this is our starting x value. Starting x value. And on top, you have little b, and this tells us where we are ending, our ending x value. The piece in the middle, this f of x, this is the function to find the area underneath. And this last piece of the integral is this dx, and this tells us what variable is changing value to produce us accumulating area. So what variable is changing to produce area accumulated? I'm going to pause for a second. You should probably copy this down. Go ahead and pause the video. And then another thing you need to know is when we do the process of accumulating area using integrals, this we call integration. So the process is integration. This is the process. So for example, we have a function over here. We have speed on one side, time on the other. Let's say it's going from 0 to 10. And so if we're going to cut that off here, we want to find the area under this. Let's call this f of x. How we would write the integral for this is we'd say the area under the curve is equal to integral symbol. We're going from 0 to 10, so our starting value is 0, our ending value is 10, so that's where we decided to cut it. Whatever function that is. And then with respect to x, that's where the dx is. So we are integrating from 0 to 10 of f of x with respect to x. So just again, recalling what area means is looking at two different example graphs. Is here we have area going again 0 to 10, chopping it off here. We don't care about the area afterwards. That is signified in our indices 0 and 10. Or we could have something in like this where we're only going from 3 to 4. So we're only talking about this small piece of area. So really, we're just accumulating area between two, in this case, x values. Okay, I'm gonna let you pause for a second, do a little bit of processing. All right. So yesterday or today, depending on when you're watching this, in class, we approximated area by summing up rectangles. So if we have this nice graph that you see 3 times over, we would, let's say, take the area from 0 to 10. Let's call this 10. And we would approximate area is equal to 0 to 10 f of x dx, which was approximately equal to the sum of the rectangles that we draw in. So if we start off by drawing, let's say 1, 2, 3, 4, 5 rectangles, maybe it's just gonna be 4. 1, 2, 3, no, I counted right, 4, 5, we get an okay area. Like, you know, it's not bad. We have like a little bit of overestimate, but you know, it's not terrible. And we have seen that yesterday or today, Tuesday, Wednesday, we have seen that the number of rectangles we use, the closer the area gets to the true area. So instead of using 5, let's say, what if we use 10? This gets a little tedious. Oops, I think I just switched endpoints. 1, 2, 3, 4, 5. I think that's 10 again. But we see as these rectangles are getting smaller, our area is less of an overestimate. So if we go even smaller rectangles, and obviously I can't draw an infinite number of rectangles because I am a human. But if we draw infinite rectangles in this same interval, we should get the true area. So if we let the number of rectangles go to infinity, then we should get the true area under the curve. And I'd like you to keep this in mind. I'm hoping that makes you think of something we studied earlier in calculus of how can we let something go to infinity. Okay, take a second to process, because we are about to do a short sidestep / pre-calc honors review. What we are going to review is summation notation or sigma notation. We use summation notation to express large sums in a short amount, in a short form. So we have the sum, this is sigma of the term a sub k going from 1 to n. So we're adding up a sub 1 plus a sub 2 plus ... forever a sub 3, a sub 4, a sub 5, a sub 6, until we reach a sub n minus 1 plus a sub n. So again, the k tells us where to begin. What number are we starting at? Where to begin. And the n tells us where to end. Where should we stop adding? Now, if n is equal to infinity, if it's appearing above the summation, this tells us that the terms go on indefinitely. Definitely. There we go. That's how you spell the word. And this is going to help us with our calculus of summing up infinite number of rectangles, because adding up lots and lots of rectangles would take like a lot of space. So instead we want to use summation notation. So, apologies, I need to get my papers ready. All right, so here we have another function for which we want to find the area under the curve from A to B. And if you see at the axis here, this is A plus delta x. So this is saying that the amount of change between these two is delta x. So the amount of change between the next two pieces should be 2 delta x. So this next one is a plus 2 delta x. This next x value is a plus 3 delta x, and so on and so on and so on until we get to b. So if we want to find the area from a to b using rectangles, well, what would those rectangles look like? If we use a as one of our endpoints, ooh, I used too many colors. Okay, I'll go purple right now. A is an endpoint. This is, oh, it's dying on me. That's unfortunate. Sorry, folks. Blue, so this is our rectangle here. Well, the area of this rectangle would be, if we're using a as our endpoint, well, that's, the height is f of a, and the width is delta x, plus, let's use this next rectangle as our endpoint. Our height would be the value at a plus f of x. That's a plus, not an at sign. F of a plus delta x times the height, or sorry, the width, delta x, plus another rectangle. Now we're using instead f of a plus 2 delta x as our height, times our width is still delta x, plus, and you can see I'm running out of room on my paper. So this is gonna go on forever until we hit the last rectangle. Now note, this last rectangle, we didn't use b as our height value. We used the one right before b. So instead of writing f of a plus n, or f of b, we're gonna write n minus 1 because we don't know how many rectangles are in here. We just know it's one less than the number of subintervals. So this would be broken into n subintervals, n rectangles. And we have one, we're using the one fewer as the height here. We're using this as the output times still our width delta x. So that is a lot. So instead we want to just use a Riemann sum to write this more compactly, because we don't want to rewrite this every single time. That would be a lot. So instead we'll say that the area is approximately equal to the sum from k equals 0, because we have no delta x in our first height, to n minus 1. That's where we ended. Now each term has a delta x in it. So what we're really writing here is, how do we find the area of each rectangle? We have the width, delta x, times the height. F of, well, all of them have a's, a plus, and almost all of them have delta x's. Oops, this one should have delta x too. Delta x times, but the first one doesn't. So how can we get delta x to not be there for the very first one? Well, if k starts at 0 times k, delta x times k. So again, we're using a Riemann sum to express the area here to make it more compact. We are setting our first index to start at 0, so that when we plug in 0 here, this delta x changes and we just have f of a. So we're using our leftmost endpoint as our first height times the width, and the width stays the same for every single rectangle. We could do this with right endpoints. We would just end up changing the inside notation just a little bit. And I will leave that for you to play around with. Okay, so this is saying the area under a curve is really equal to delta x, our width, times, well, this right here is just f of x sub k, the k most x value. And we're still going from k equals 0 to n minus 1. So what are we going to do with this? Why are we using a Riemann sum? What is the point? Well, first the point was to move from writing lots and lots and lots of terms to just writing one term. But remember that we started off this quest because we wanted our rectangles to approach infinity. And so we can use the idea of a Riemann sum and this idea of the number of rectangles going to infinity, put them together to get the true area of the curve. So as we go from just a couple rectangles to infinite rectangles, the limit of this sum is the true area under the curve. Area equals the limit as n is approaching infinity of our Riemann sum right here. Notice we have n is approaching infinity, so we're letting the number of rectangles, our stopping point for the sum, to go to infinity. Yes, infinity minus 1 is still infinity, it's just a different type. Now, how does this connect back to integrals? Remember that area under the curve, really we're talking about the integral from a to b of f of x. If we're calling this a, this b, a and b is equal to this limit. You might be asking yourself, how do these a and b show up in your Riemann sum? Because I don't see any. I see an f of x, I see an f of something. I see this delta x, but I don't see any a's and b's. So what we're gonna do next is we are going to evaluate integrals as limits of Riemann sums by going back and forth. Like, how can we write a definite integral as the limit of a Riemann sum and vice versa? So I'm gonna do one example going definite integral to limit and one example of limit to definite integral. And then I have 4 for you to try on your own, of which I will post the answer keys to, and you can check in class. Okay. So the first thing you need to know is that delta x, well, that is really talking about taking this interval from a to b and splitting it into n subintervals. Split into n equal subintervals. And you can think about this as like slicing up a loaf of bread that's 10 centimeters long. If you're starting at 0, you're going to 10. If you had 10 friends, how big would each slice be? 10 divided by 10. So n is the number of slices you're having. So if you're going from a to b instead, and you're splitting into n subintervals, it's really b minus a, that distance, b minus a, divided into n subintervals. And that is the width of each rectangle. So that's our delta x. So knowing that piece, it's much easier to connect the integral to the limit. So the first thing I do when I look at this integral and I'm trying to write it as a limit, I'm going to write out all of the pieces I need. One of the pieces I need is delta x. Delta x is equal to b minus a over n. What's my b value? 4. What's my a value? 1 divided by n. Do we know how many subintervals there are? No, we want them to go to infinity, so it's going to stay n. 3 over n. The next thing is looking at our limit definition. So we've got delta x, check. We need f. What is our function here? X to the 5th. So f of x is equal to something to the 5th. F of a plus k delta x, that's the inner bit here. K we need, that stays. We know delta x. Do we know a? Yes, we do. It's 1. So 1 plus k times 3 over n. So we've got our inner bits. So we've got our inner bits, we've got our 3 over n. We're ready to start plugging in. We always write limit as n is approaching infinity. The sum of, I'm going to start at k equals 1 instead and now go to n. It is the same as going from k equals 0 to n minus 1. And we'll go 1 plus k times 3 over n, all to the 5th. That's our f of a plus k times delta x times delta x 3 over n. So we're going to take the sum of, this is our width, times the height of an infinite number of rectangles. And that will give us the true area under the curve for the function x to the 5th from 1 to 4. Now, how do we go the other direction? Here we have the limit as n is approaching infinity. I'm sorry. As n is approaching infinity of the sum of k equals 1 to n. This is all normal so far of f of 2 plus k, that's also should be there, times 3 over n, okay, times 3 over n again. So when we're dissecting this, we're looking at f of something times 3 over n. So this times 3 over n, that gives us a clue about what our delta x is. Delta x is equal to 3 over n, which should be equal to b minus a over n. So then we know that b minus a is equal to 3. Now this tells us our f of a plus k times delta n. Okay, so k is going to stay the same. We know this is our delta n, delta x. So what is this 2? 2 must be a. So we have b minus 2 equals 3. So b must equal 5. So from here, this is what we've got to write our integral. We have the integral from, we said this was a, 2 to 5 of something. Now what goes in the inside? What's the function? Well, it doesn't actually tell us. It just says f of something. So f of x is just our function with respect to x. This has been a lot, so I'm going to let you pause, process, do what you need, send me an email, come to Flex on Monday, October 28th. But I would like you to also try these 4. So take the limit, go to write it as a definite integral, take the definite integral, write it as limit. This is 2 to 4. Take the limit, write it as a definite integral. Give it a try. If you're struggling and you want to meet before Monday, 10/28, email me, see when I'm available, and we can talk. I'm excited to start class on Thursday with a little bit of this and then move on towards evaluating integrals more efficiently so we don't have to do a limit definition every single time. All right, I hope you have a wonderful rest of your day. See you tomorrow.